Hello, AP Physics C students. You should have already looked at the previous post that led you through a derivation of an equation to find the magnetic flux, total magnetic flux, through a rectangular loop of wire that's some distance away from a current-carrying wire. So now what I need you to do is look at problem 7, where you're basically going to be applying that idea to this situation. So I want you to start from scratch, rederive the equation. If you need to look at the previous post to look at the steps, great. Try it on your own first, maybe, then go back and refer to it. But the point is you need to be able to derive an equation that follows this particular format, problem 7, part A, and then put the numbers in and see if you can find the answer. Then come back to this and see if you did it correctly. Okay, I'm not going to go through the whole derivation here, but when you put all the numbers in, we should get an equation that looks something like this. So here is actually mu naught over 2 pi. I just took out the 2 pi part, so it's just 2 times 10 to the negative 7th, where normally it's 4 pi times 10 to the negative 7th divided by 2 pi, so I just got rid of that. The current is self-steady at 3.4 amps. This is the 0.05 meters. That's the length that's parallel to the direction of the moving charges in the conductor. That's the part that's not changing as you change the flux through the loop, going to different distances. And then you should have a natural log term that has the difference between the far distance, in this case that's 9 centimeters, or 0.09 meters, divided by the close distance, that's the 6 centimeters, or 0.06 meters, for a ratio of 1.5. And when we put all the numbers in, we should be getting 1.4 times 10 to the negative 8th Webers. If anything about that went wrong, go back, see what you did wrong. Again, refer to the previous post, see if you got the same equation, see if all these parts here look like they're in the right places. All right, then you're going to go ahead to part B. Try part B on your own, then come back to the video after you've already tried it. Okay, so I'll break it down step by step. Now, the current is changing in the wire, which means, of course, the flux is changing through the loop. We know from Faraday's law, anytime flux changes, that induces an EMF, and that's going to create a current inside the loop. So we start, of course, with Faraday's law, negative N d phi dt. Here we have a function for phi, so you don't have to worry about whether the field is changing, or area is changing, or the angle or orientation is changing. We have a function for phi, so we're just going to differentiate that function with respect to time. I took the n out because already, it's just one loop, so n is 1. We still have the negative sign, that's rather important, and this should be the function that you derived back in part A based on the total flux through this rectangular loop. Here I've just written this as 1.5 rather than constantly writing 0.09 or 0.06 because those dimensions aren't going to change, so that's just the ratio of 1.5 there. So as always, we want to pull all the stuff to the outside that's not changing and only think what's changing. Well, mu naught and 2 pi, of course, they're not changing. L, that's the 5 centimeters, that's not changing. Log of 1.5, that's the dimension of the loop, that's not changing. It is I that is changing, and you're given the function of I with respect to time. So we pull all those other things to the outside. It is then just a differentiation of I with respect to time, and you have a very simple function. It's 3.4 amps minus 0.06 amps per second times time. Just differentiate that with respect to time. That should be negative 0.6 amps per second, and then it's just a matter of putting all the right numbers in the right places here, and we should be getting the EMF of 2.4 times 10 to the negative 9th volts. But that's still not the answer, right? Read the problem carefully. That's for the current in the loop. Now, be very, very careful. Even the word loop is underlined to remind you the current through the wire, that's the function that's given to us, 3.4 amps minus 0.6 amps per second times time. That's what's changing, causing a changing flux, which induces an EMF in the loop. That's going to create a current in the loop. So how do we find that? Well, you're given the resistance of the loop. Ohm's law, right? EMF over R equals the current. The EMF is 2.4 and 10 to the 9th volts. The resistance is given as 0.4 ohms. We should be getting a current in the loop of 6 times 10 to the negative 9th amps, or 6 nanoamps, if you want to write it that way. But that's fine too. All right, if you haven't yet, go on to part C. Try that on your own, then come back to the video. Okay, so we're going to try to see what's happening at different moments in time, 3 seconds and 6 seconds. I'll break it down step by step. First, we want to find what the current is at 3 seconds. You put the 3 seconds into the function, which is giving 1.6 amps. Why is that important? We want to know what direction the current is pointing. Here we're using air quotes. You can't see it. I'm using air quotes, of course, because current is a scalar, but in other words, which way the charge is flowing, right? And so, according to the picture, the charge is flowing to the top of the page. We're getting a positive current, we'll say, that's pointing the same way as it was originally, considering the original was 3.4 amps, and so the charge is flowing to the top of the page. What is happening, though, is that dIdt is negative, right? So the current is decreasing. So just like in the previous problem, the current is decreasing. We're going to deduce the current. In fact, this is the exact same situation as part B, but we now have to go through our usual Lenz's law sort of ideas, right? The initial direction of the magnetic field, the change of the magnetic field, the induced magnetic field, and then what direction of the current is in the loop. Remember, whenever we do Lenz's law, we're finding the induced current. This here is the current in the wire, not the current in the loop. This is the induced current in the loop over here. So if you didn't get this far, try Lenz's law on your own, pause the video, come back. Alright, so we figured out that the current is still pointing in the same general direction, and so we have to figure out the direction of the field produced from the wire in the general vicinity of the loop. So we have to do a right-hand rule. Okay, so which one is it? Is it the point, the grab, or the shortcut? This is the grab. Anytime we're finding the field produced by a wire, we're grabbing the wire. So with the right hand, you grab the wire. Remember, my suggestion is you put your imaginary wire, your pencil or pen, right up against your paper. You try to grab it, and then you'll have a very physical sense of how your fingers are touching the paper on the right-hand side. So the initial direction of the field is into the paper from the wire. What's happening, though, is that the current is decreasing in the wire. So the field is decreasing, and so the change in the field is out of the page, right? The initial is into the page. We're taking field away, so the change is out of the page. The universe doesn't like that. It's going to try to put the field back into the page. And now we've got to figure out the direction of the current that would produce this induced field. So which right-hand rule is this? This is the shortcut. We want a field that points into the page. We've got to figure out whether it's going to go around clockwise or counterclockwise. You point your fingers in the direction of the current that would make your thumb point into the page. That should be in a clockwise direction, and so the charge is going to flow around in a clockwise manner to create a field that opposes the change because the current in the wire is changing. Okay, if you weren't quite sure how to do that in part 1 here, pause the video, try the whole thing again for part 2, then come back to the video to see how I did it. I'm going to go through the same steps here. Okay, so the current in the wire at this moment is negative 0.2 amps, and that's important because now the current has changed direction, right? If originally it was pointing at the top of the page, now the charges are flowing in the other direction to the bottom of the page. dIdt is still negative 0.6 amps per second. That's a constant change in the current. So the current value is increasing, but it's in the opposite direction to the original, right? So negative 0.2 and then negative 0.8 and so on and so forth. It's getting more and more negative, or it's still pointing at the bottom of the page, but a larger and larger current. So when we wrap our fingers around the wire, grabbing the wire, our fingers are now pointing out of the page. The initial direction of the field is out of the page because the charges are pointing the other way, and that value is increasing. So it's getting more and more out of the page. The universe doesn't like that, so it tries to induce the field into the page, making the current in the loop point clockwise, and once again, we have the charges flowing around in a clockwise direction. It's all just Lenz's law, over and over. Alright, now we're going to go ahead to problem 8. Go ahead and read problem 8. If you just do part A on your own, and come back to the video to see how I do it, and then just in case you're on the wrong track, you'll know if you're doing correctly for parts B and C. Okay, so this is putting together a lot of things. It's a Lenz's law problem, but now it's involving solenoids. Right, so one of the first things you want to do with a solenoid is figure out what the direction of the current is in. And so here we have our source of voltage, and we just sort of trace the charges around. We know they're coming out of the positive terminal, and then you look at the windings of the wire around the core. You see it passes behind the core first, and then comes down in front. And you should be able to see the charges are always pointing to the bottom of the page in these parts of the wire that are close to us. This is always the first step when you do a solenoid problem. Trace the charges around. Alright, now we need to know the initial direction of the field produced by this solenoid. So you can do this a bunch of ways. You could do the grabbing of the wire. If you're going to do that, you want to grab the wire close to you, which is why we identified the currents in this part of the wire close to you. And remember, all we care about is the field in the interior of the loop of wire, in the interior of the solenoid. So when you do that, you want to stop your fingers when they get inside. Alternatively, you can use the right-hand rule shortcut, which I find to be a little bit simpler. So you are going to wrap your fingers around the core, pointing the way the direction of the charges are flowing here, and we stick our thumb out, we should be getting the direction of the field within the solenoid, which is all we care about, is to the right. Okay, so you know the initial direction of the field in the location of solenoid 2 is to the right, because it's produced by solenoid 1. Then we read the problem. It says solenoid 1 is moved to the right. So the whole thing is getting closer to solenoid 2. Does that mean the field by solenoid 2 is getting stronger or weaker? Well, the other electromagnet is getting closer, so of course it's getting stronger. So we're increasing the field near solenoid 2. The universe doesn't like that. It induces the field pointing the other way to try to remove the field, the increased field. And then it's a matter of figuring out which way charge is going to flow around this solenoid to make a field that points to the left. So here's where our right-hand rule shortcut comes into play again. We want the field produced by this solenoid to point to the left. So you point your right-hand thumb to your left, wrap your fingers around. We should see the charges are all flowing to the top of the page in these near parts of the wire. follow the charges around here, and we should see the charges are flowing to the left inside the resistor in solenoid 2. So those are the steps you follow. So try it then for parts B and C, and come back to the video where I'll go through the solutions. Alright, part B, the switch is initially closed, and so it's producing charges that are flowing around this way, and they're again pointing to the bottom of the page in the near parts of the wire, producing a magnetic field pointing to the right. And then we open the switch. Right? So the initial field is pointing to the right in the location of solenoid 2. When we open the switch, this field goes away. So we're taking field lines away, and so the change in the field is to the left. Right? If it was to the right, we're taking all those field lines away. They're pointing to the left. The universe doesn't like that and says, look, you just took my field away. Let's put it back. Right? So we create a field pointing to the right inside solenoid 2. So now you wrap your fingers around, so your thumb is pointing to the right. Charges should be moving to the bottom of the page. Follow those charges around, and they should be pointing to the right. Charges pointing to the right inside the resistor in solenoid 2. Alright, for letter C, the switch is initially open, which means there's no field produced at all, then it's suddenly closed. So here's what happens. When it suddenly closes, the charges are flowing around here to the top of the page, but look at the windings. The windings are now different. The charges are coming out of here, but they're pointing to the top of the page because the wire wraps around the coil first in front, which means if you do your right-hand rule shortcut, the field within the interior of the solenoid is pointing to the left. The initial field was 0 because this switch was open, and all of a sudden you create a field to the left in the vicinity of solenoid 2, so all of a sudden you put a field to the left. The universe doesn't like that and say, look, there used to be no field here, you put a field there, let's try to take it away by producing a field to the right. And now the field in solenoid 2 is going to point to the right. You wrap your fingers around, and you see the charges are pointing to the bottom of the page in the parts of the wire that are close to you. Follow those charges around, and now the charges are moving to the left in the resistor in solenoid 2.